So let's do some numerical examples from chapter 13. So the first one that we'll do is problem number 5, and it's on page 357. So let's read the problem. The star Rigel radiates most strongly at about 200 nanometers. What is its temperature, and how does that temperature compare to the sun? We will use Wien's law. Which says that the maximum temperature that is radiated, the maximum wavelength that is radiated times the surface temperature of the star is a constant 2.9 times 10 to the 6, as long as you measure the wavelength in nanometers and the temperature in degrees Kelvin. So if we divide both sides by lambda max, then we see that the temperature is given by 2.9 times 10 to the 6 divided by lambda max, and in this problem they tell you that the lambda max is 200 nanometers. So this is equal to 2.9 times 10 to the 6, and 200 is 2 times 10 squared. And if you divide 2.9 by 2, you get 1.5. Now, 10 to the 6 divided by 10 to the 2 follows the rule that a to the n divided by a to the m is a to the n minus m, so this is equal to 10 to the 4th, so the answer is 1.5 times 10 to the 4th degrees Kelvin for our answer to that problem. They want to know how this compares to the sun, so this is about 15,000 degrees, and the sun, our sun is at 5780 degrees Kelvin, which is approximately 6,000 degrees Kelvin. So you see that this is 2.5 times hotter than sun. So that's our answer, 2.5 times hotter than the sun, and the surface temperature is 15,000 degrees. So next on the same page, we will go to number 6. And it's an absolutely identical problem, except that the temperature, the strongest wavelength is now 500 instead of 200, but everything else stays exactly the same. So we go now to problem number 6 on page 357. And again, we find that the temperature is equal to 2.9 times 10 to the 6 divided by the lambda, so it's equal to 2.9 times 10 to the 6, and the lambda maximum that they give us in this problem is 500. So this is equal to, let's see, the best way to do that, set up that arithmetic, is 2.9 times 10 to the 6, and this is equal to 0.5 times 10 to the 3rd. So 0.5 goes into 2.9 about 6 times, and 10 to the 6 over 10 to the 3rd is also 10 to the 3rd times 10 to the 3rd. So this is about 6,000 degrees, and our sun is at 5780. So the surface temperature of this star is near identical to the surface temperature of our sun. So the next problem, number 7, page 357, number 7. So to read the problem, Arcturus is about half as hot as the sun, but is about 100 times more luminous. What is its radius compared to the sun? The Stefan-Boltzmann law is that the luminosity of any star is equal to Stefan-Boltzmann's constant times the temperature of the 4th degree and it's times the surface area, which is 4 pi r squared. So this is true for any one star that you care to look at. And since we're interested in Arcturus, then we will label these by A. The radius of Arcturus, the temperature of Arcturus, and the luminosity. Now the luminosity of the sun is also Stefan Boltzmann's constant, and the temperature of the sun to the 4th degree is 4 pi r sun squared. And if we divide one equation by the other, then you'll see that on the left side we get what we asked for, which is the ratio of the, well, the ratio of the luminosities is given. So on the left side we're going to get L of A over L solar. And now we have some items that cancel out. These cancel out, the 4's cancel out, and the pi's cancel out, so that it is equal to the temperature of Arcturus over the temperature of the sun to the 4th power, because we know that TA to the 4th over T sigma to the 4th is just equal to TA over T sun to the 4th power, because the fact that, let's see, best way to say this is that A to the n over B to the n is the same as A over B to the n power. So this is a law of exponents. And the same applies here, that this is the radius of Arcturus over the radius of the sun to the squared power. Now in this problem we're given some of these proportionalities. For example, we're given that it's half as hot as the sun, but is about 100 times more luminous. Well, if Arcturus is 100 times more luminous than the sun, then this number is 100. And if it is half as hot as the sun, then this number is 1/2 to the 4th power. And we have RA over R sun, which is what we're looking for. So now what I'm going to do is say that 1/2 to the 4th power is 1 over 2 to the 4th. And that is equal to 1 over 16. So it's 1 over 16 times RA over R sun squared. And now to multiply both sides by 16, then on the right side, these will cancel, and on this side we get 1600 is equal to RA over R sun to the square power. And now when we just take square roots of both sides, the square root of a square is just the object itself, so the ratio of RA to R sun is the square root of 1600, which is 40. So this star has a radius 40 times that of the sun. So, problem number 8, same page. Now remember, you can freeze the frame and look at these for as long as you want. So page 357, number 8. To read the problem. A stellar companion of Sirius has a temperature of about 27,000 K and a luminosity of about 10 to the minus 2 solar luminosities. What is its radius compared to the Sun's, and what is its radius compared to the Earth? Well, the luminosity of this Sirius companion is equal to sigma T Sirius companion to the 4th power, 4 pi R Sirius companion squared. And of course, the luminosity of the Sun is equal to sigma T Sun, 4th power, 4 pi R radius Sun squared. And if we divide one equation by the other equation, then we see we have certain cancellations. For example, the sigmas cancel, the 4's cancel, and the pi's cancel. So what we're going to ask for is the radius, and we're given some other pieces of information. So that the ratio of the luminosities is given as 10 to the minus 2. It's about 100 times 10 to the minus 2 is the ratio of the luminosity of this companion to the luminosity of the sun. And the temperature of this companion to the temperature of the sun, it's about 1/2 as hot. So the ratio of these temperatures is 1/2 taken to the 4th power, and we're dealing with the radius that we're looking for over the radius of the sun, quantity squared. And here we're using freely the fact that a to the n over b to the n is equal to a over b, all to the n power, which is a rule of exponents. So what I'm going to do now is take the square root of both sides, and the square root of 10 to the minus 2 is 10 to the minus 1. And the square root of the 4th power is a square power. And the square root of a square is just the object itself. So we've simplified things by doing that. So here we have 10 to the minus 1, and 1/2 squared is equal to 1/4, and this is RSC to the R sigma. And something went wrong here. I mixed up two problems. I was mixing up problem number 7 with problem number 8, so that's not going to work. So I'm going to do a complete restart, page 357, number 8. A stellar companion has a temperature of 27,000 and a luminosity of about 10 to the minus 2 solar luminosities. So the luminosity of the stellar companion is sigma t stellar companion to the 4th and 4 pi radius sigma stellar companion squared. Luminosity of the sun is sigma t sun to the 4th, 4 pi radius of the sun squared. And again, dividing one equation by the other is going to produce a cancellation of these terms, and it's going to result that the ratio of the luminosities, which is given as 10 to the minus 2, is equal to TSC to the 4th power over T sun to the 4th power times the radius of the companion squared over the radius of the sun squared. Now, the temperature of the companion is given as 27,000. The temperature of the sun is 6,000. This is to the 4th power, and what's left is the radius squared over the radius squared. Now, these 3 zeros are going to cancel, and 27 divided by 6 is 4.5. So 10 to the minus 2 equals 4.5 to the 4th power times RSC over R sigma sun to the 4th power. And now we're going to take the square root of both sides, the square root of this object, the square root of this object, and the square root of that object. Now the square root of 10 to the minus 2 is 10 to the minus 1. The square root of a 4th power is the square. And the square root of a square is just the object itself. Now 4.5 squared is 20.25. You take the calculator and do 4.5 squared, 20.25. So we have as our next step 10 to the minus 1 equals 20.25 times the ratio that we're looking for. And you divide both sides by 20.25. And you find that 10 to the minus 1 over 20.25 is equal to the ratio, RSC over R sun. And now on the left side, to make things easier, you multiply the top by 10 and the bottom by 10, and you get 1 over 202.5 is equal to RSC over R sun. Now this is a proportionality, so cross multiplication is in effect. You cross multiply this way, and you get that the R of the sun is equal to 202.5 times the radius of this stellar companion. So this companion is 202 times smaller than our sun. And they want to know how this compares to the Earth. Now, the radius of the sun is 109 times the radius of the Earth, and the symbol for the Earth is a circle with a cross in it. So you see that this radius is 1/2 the radius of the Earth. So RSC equals 1/2 the radius of the Earth. So end of that problem. So the next problem that we're going to do is number 10. So this is on the next page. A line in a star's spectrum lies at 400 nanometers. In the laboratory, that same line is 400.2 nanometers. How fast is the star moving along the site? Is it moving towards us or away from us? Now, the shift in the wavelength, delta lambda, equals the wavelength that you observe minus the wavelength in the laboratory. And the wavelength that we observe in this star is 400, and the wavelength in the laboratory is 400.2, so the shift is a minus 0.2. The minus shift indicates the star is moving towards us. So we've already established the quantitative answer that the star is moving towards us. And they want to know with what speed, so you use the formula for the Doppler formula. The velocity of the object over the speed of light is equal to the shift in the wavelength over the original wavelength. So if we multiply both sides by c, then we have a cancellation on the left, and we just get the v is equal to c delta lambda over lambda. Now the velocity is what we're looking for, and c is the speed of light, 3.0 times 10 to the 8th, and we've determined that the shift is a 0.2, and the original wavelength in the laboratory is a 400.2. So we have to do this arithmetic, and we find our answer. We'll spell out the arithmetic in powers of 10. So velocity equals 3.0 times 10 to the 8th times 2 times 10 to the minus 1 over 4 times 10 to the squared. And I'm rounding off 400.2, which is 400. So let's collect the numbers. We have a 3 times a 2 over a 4, which is a 6 over 4. Now the powers of 10 on the top are 10 to the 8th and 10 to the minus 1. So 10 to the 8th times 10 to the minus 1 equals 10 to the 7th. Then 10 to the 7th divided by 10 to the 2 equals 10 to the 5. So 6 over 4 times 10 to the 5th meters a second. And 6 over 4 is 1.5. So 1.5 times 10 to the 5th meters a second is the speed with which the star is moving towards us. So the next question is number 14 on the same page. Estimate the luminosity of both Regal and Barnard stars using one of the HR diagrams in the chapter. So if you turn to the page that has the HR diagrams on it, then you can estimate the luminosity of Regal star and the luminosity of Barnard star, or you can steal them from the table at the bottom of the page. And the Regal luminosity is 100,000 solar luminosity, and the Barnard star is 10 to the minus 3 solar luminosities. So to continue, the temperatures of these two stars are also either estimated from the charts, the HR diagram, or stolen from the temperature at the bottom, chart at the bottom of the page. The temperature of Regal is 12,000 degrees. The temperature of Barnard star is 3,000 degrees. So that's our input data. And calculate the radii as both stars compared to a solar radius. So in terms of solar radii, so now we're doing page 368, number 14. So first we'll do Regal. And the luminosity of this star in units of solar luminosity is equal to its, well, let's do it correctly. We'll put on one and then we'll do the other. The luminosity of Regal is equal to 7 Boltzmann constants times the temperature of Regal to the 4th power, 4 pi, radius of Regal to the square power, but that of the sun is equal to sigma T of the sun, 4 pi, radius of the sun squared, and might as well use the symbol for the sun at this point. And we have the usual cancellations of the constants, they're gone. So the luminosity of Regal to the luminosity of the sun is given as 100,000. And the temperature of Regal is given as 12,000 degrees. And the temperature of the sun is known as 6,000 degrees to the 4th power. And this gives you the radius of Regal over the radius of the sun to the power squared. Now we do some cancellation of these zeros. 1, 2, 3, and 12 over 6 is exactly equal to 2. So we have 100,000 equals 2 to the 4th power times what we're looking for to the 2 power. So we can either take square roots at this point, or we can continue. So why don't we just continue? 2 to the 4th is 16. So 100,000 equals 16 times what we're looking for. And so this comes down on the bottom of the other side. 16 equals the ratio of what we're looking for squared. And if you take your calculator and divide 100,000 by 16, you get 6250. So 6250 is equal to what we're looking for to the square power. So what you do is take square root of both sides. And the square root of 6250 is 79. So 79 is equal to the ratio of the radius of the Regal star to the radius of the sun. And they say to compare this with a diagram that gives the different radii, which is on 351. And if you look for the Regal star on 351, you will find that it comes in at about 90. So this compares very favorably with the 90 that you find from off of the chart. So now what we're going to do is do the Barnard star. And the start is the same for the Barnard star. The luminosity of the bar Barnard to the luminosity of the sun. And after we have our usual cancellations, it's going to be the temperature of the Barnard to the temperature of the sun to the 4th power, the radius of the Barnard, the radius of the sun to the squared power. And now we have the given information that the luminosity is 10 to the minus 3. So it's 0.001. And the temperature of the Barnard star is 3,000 degrees. The temperature of the sun is 6,000 degrees to the 4th power. And this is what we're looking for. So we have our usual cancellation of the zeros. And so 0.001 equals 1/2 to the 4th power times what we're looking for. And 1/2 to the 4th power is 1/16. So 0.001 equals 1/16 times what we're looking for. So we're going to multiply both sides by 16, and we get 16 times 10 to the minus 3 equals what we're looking for. And we're going to change this to a 1.6 times 10 to the minus 2 equals what we're looking for. Same thing. And now we're going to take 1.6 times 10 to the minus 2 equals RB over R sun, quantity squared. And we're just going to take the square roots of this. Now the square root of 1.6 is 1.27. So 1.27, the square root of 10 to the minus 2 is 10 to the minus 1, and the square root of a quantity squared is just the thing itself. So we have that point 127 is the radius of the Barnard star to the radius of the sun for an answer to the question. And if you go to the chart on page 351, you see that you read it off of the chart as 0.95. which compares very favorably to our calculated result. So the last question that we're going to do is number 15. If a main sequence star has a luminosity of 5,000 solar radii, what is its mass in relation to the sun's? All stars in the main sequence, this is number 15, page 358. All stars in the main sequence obey the mass-luminosity relationship, that their luminosity measured in solar luminosities is equal to their mass measured in solar masses. And here we are given that their luminosity is 5,000 solar luminosities. So that is equal to their mass in solar luminosities to the cube power. So we want to find, as our answer, their mass. So what we have is their answer cubed. So if we take each one of these to the 1/3 power, then because a to the n raised to the m power is a to the n times m, that means 3 times 1/3 is just 1. So we get the m by itself, and now what we want is the cube root of 5,000. So we need 5,000 to the cube root, so you ask the calculator, what is the cube root of 5,000? And a good way to do that is to type in 5,000, then type in your power key, and then type in 0.3333 as the third root. And the answer that you will find is 17.1. So this star has a mass of 17.1 solar masses, which means that it's fairly high on the main sequence.